Now let's actually figure out what they are. And I'm going to put this red up here because that's the square root function on top, right? And then this one right here is the y equals x, which is that one on the bottom. Agree? Okay. So as I move the rectangle from left to right, I always have red on top, black on bottom. That means my outer radius is always going to be the distance from here. So here I am standing, I get my measuring tape, I measure, and what is the distance from here to here? So it's this distance from here to here first, which is 4. It's like the absolute value, right? You don't put -4, you put 4. Okay, so the distance from here to here is 4. And then the distance from here to here is the top one, right? Root x. So our outer radius is 4 plus root x. That's our outer radius. And then what about our inner radius? Okay, we know that from here to here is 4, and then from here to here that's just x. So the inner radius is 4 plus x. Point something out. If I was asking you to find, to take the region bounded by these two curves, let's say from 1 out to 3, then I'd be talking about a region over here, wouldn't I? Like something in here, wrap that. That would change this, wouldn't it? Because now your top and bottom would switch places. So just keep that in mind. It just depends on where we're looking. We're only looking between 0 and 1, so we maintain that the red is on top of the black the whole time. All right, that's it. That's our inner radius. So now we just go to the formula. The formula is pi integral where to where? 0 to 1. Okay, the outer radius squared. 4 plus root x in parentheses squared minus the inner radius, which is 4 plus x, that quantity in parentheses squared, all of that dx. And remember, if you actually wanted to do this integral, you'd have to square that. Like you'd have to FOIL it out, right? This is not 16 plus x. You don't just square each one. You have to FOIL it. Here you have to FOIL it. Then once you did that, wouldn't they all just be powers of x? And then you could integrate term by term and you could get it. Be a little messy, but you know, relatively speaking, it could be done. So we're done? That would be the volume if we wrapped it around the line y equals -4. Let's do another one. I want to wrap it around the line y equals 3. This will be part E. Seems like time's going very slow here today. I'm not in a hurry, it's good. I've got a lot to talk about still. I don't know if this comes across or not. This isn't really even relevant, what I'm about to say. I don't know if this comes across when I'm up here talking about this, but the reason I don't really have formal notes for this is because I like to explain it exactly the way it makes sense to me. Like this is the way it makes sense to me, so that's the way I'm explaining it to you. Like if you go to the book or you go to a tutor, they're probably going to have a different approach. I'm just letting you know that ahead of time. A lot of times these things are called solids of revolution. So a lot of times what people do when they're trying to go about lines like this is they take the entire graph and they just like shift it and they move it so that this line is now the new x-axis. And so they use translations of functions in order to do this as opposed to visualizing outer and inner radius, if that makes any sense. Which I'm okay with doing that. You still get the same answer. The reason I don't like that is because I think it circumvents, it forces you to go around the visualization, which I think is much more powerful than just oh, we're just going to shift a function and you don't really ever have a picture. My opinion, all right? So, all right, draw a picture. This time I'm going to draw it kind of down here because I'm going to be up here at y equals 3. That's my axis of rotation. Forgot to draw my little rotation thing on the last one. I'm going to go a little faster on this one. I've got the root function here. I've got that function like that. So this is y is root x, y is x. Here's my rectangle. It is orthogonal to the axis of rotation. And my x-axis is down here. So I'm going to move everything over. Here's my x-axis, here's my rectangle, here's my axis of rotation. See, I even brought the x-axis over, right? You'll see what I think the importance of that is. I need to figure out what my outer radius is, right? That's the distance from the axis of rotation out to the outer edge, right there, right? So this is my R out, and then my R in is this one. Okay, tell me about this R out. Yeah, so from here to here, see with the x-axis here, I can talk about this distance, right? That distance from here to here is 3. But I'm not that far, I'm this far, right? So it's 3, take away this much. How much is this much? The bottom of that, which is x. So I know the distance from here to here is x, so that means R out was 3 minus x. The whole distance, take away x. Follow? And then the R in, well, I know the distance from here to here. What? This got messed up, sorry. That distance is root x, right? So that distance is 3. If I take away root x, I'll have this distance. So this is 3 minus root x. And we're ready to roll here. Pi, integral, where are we still going 0 to 1? Yeah, nothing's changed, right? We're still going 0 to 1. We're going to do outer squared, 3 minus x squared, minus inner, 3 minus root x squared dx. Done. Questions or comments or concerns or complaints or anything? Yes?
I have a question. On the test, are you going to have a question that's going like A, B, C, D,
Mm-hmm.
just like this?
Mm-hmm.
Do you want us to show that much work for every single one?
I would say that if you're just going to give me the answer, do it at your own risk. Because if you give me the wrong answer without a picture, I'm going to take all the points off. If you give me a picture and I can see that your picture's good, you just kind of messed up this, then I'm going to take less off. So really, I'm not asking you to evaluate the integral because I want you to take your time in constructing a picture. If you trust that you can do all the picture in your head, like I said, just at your own risk. Is that fair?
Yeah.
Okay.
I have a question.
Yes.
On the test, are you going to ever put one that's like from like A to C and then C to D as the number of
You have to break it up. For rotating around, it'll just be a nice clean region. Yeah, it's not going to like change from one to another, like to where you have to change, no. All right, I wonder if I can do this next concept with just doing part F and seeing if we can figure it out without having to go through an entire development of the theory. Let's see. What do you think I want to do right now? Okay, so instead of doing rotate around a horizontal line here, below or above the function, how about rotating about a vertical line that's either to the right or to the left of the function? So you know how we've gone around the y-axis? Why don't we go around some other vertical line? right? Okay, so let's stick with this same example, and let's do part F. I put a little star next to this because, I mean, we haven't really technically talked about this. Volume about, how do we define vertical lines? Not y equals, we put x equals, right? Let's go x equals negative 10. Negative 10. I'm going to draw a picture. But I'm going to go way out here to negative 10. Right? I'm going to leave some space below my graph because I'm about to draw another dotted here. I'm going to bring the y-axis here, and I'm going to have a rectangle over here. So I'm going to be doing the same sort of game that I've been playing here. I've got my y equals x. I've got my root x. And now I'm trying to wrap it this way, right? So my axis of rotation, I need it to be orthogonal to my rectangle, right? So I guess now would be a good time. The method that we've been using has kind of a technical name. It's called the method of washers, all right? Because we drew washers, right, when we first established it. It's called the method of washers. To find volumes of solids of revolution, we use this thing called method of washers. Anytime you use method of washers, your rectangle must always be orthogonal to your axis of rotation. So if I want to use washers for this, I need to draw my rectangle orthogonal to this. All right, so let's draw it. Here it is. And when you do that, you have to verify that you can rewrite these as functions of y instead of x, which we've already done, haven't we? So we know we can do that. We know the function on the right always stays the same, and the function on the left always stays the same when you move this rectangle up and down. We are going to go from C to D, 0 to 1, all right? We got to wrap that thing. Crap. Okay. So let's do this. I'm going to bring this dotted line down. I'm going to bring my y-axis down. And I'm going to bring my rectangle down like that. Now this curve right here, to the right of it, is which curve? Y equals x. X equals y is the way I'm going to look at it. That's my right curve, the one on the right. And then the curve that's on the left side is, which one? X equals y squared, right? That was me taking this and solving it for x. Outer radius. You're standing here and looking out that direction to the far edge of the rectangle, which is out here, right? So let's see what that distance is. All the way to there. That's RO. What is it? It's 10 plus that distance, and that distance is y. So this is 10 plus y. And then the R inner, which goes to that edge, is again 10, right? 10, this distance, plus that distance, which is y squared. So 10 plus y squared. And then it's just the same setup, right? Pi. Integral. 0 to 1, but that's 0 to 1 this way, right? Yeah. Okay, and then outer radius squared. 10 plus y squared minus inner radius squared. 10 plus y squared squared, and then all of that dy. There we go.
So,
Yes?
so on the test, just that's it?
That's it. In fact, I don't want you to even square these because it'll be harder for me to grade it. Just leave it exactly the way it is.
So you would just leave it as like the equal dot, dot, dot.
Yep. Yep. All right. One more, and then we're going to move on. We have time to move on. Let's do part, what, G? Part G, volume about x equals 7. I mean, once this kind of clicks, you know, it just kind of, I don't know, hopefully it makes sense and it's just like, oh, okay. Not a big deal. Just take your time, make sure you draw your region correctly, right? That's very important. If you draw the wrong region, all your problems are going to be wrong, right? All right, so when I do this time, I'm going to go this way quite a bit. This is 7 out here. And then I have my this, and then I have my this, and we've done this enough now. My axis of rotation needs to be orthogonal to my rectangle, so my rectangle's this way, right? And then I'm going to wrap it like this, like around here like this. So I'm going to come down here, I'm going to draw my y-axis, my axis of rotation, my rectangle. I'm going to label these edges again. I don't remember what they were, though. It was y squared was this one, right?
Yeah.
Okay, so this one right here was x equals y squared, and then that one right there was x equals y. Who wants to volunteer, just come up here and label the rest of that for me? No, just labeled, I want the graph labeled. I'll take it into consideration.
Shit, I'm gonna try. I mean, just go upstairs. Yeah. Okay, so.
Okay, I'll give extra points, but if you get it wrong, I'll take points away.
Okay. Okay, so we're standing here. So why are we standing? This is the outer one.
Yeah.
No.
I think I get what you're talking about.
Don't judge.
Yeah.
This equals the outer one. So then.
Or it could be Batman. Or it looks like a bat, kind of. Okay, go ahead. I'm making fun of your squigglies.
So this one is y squared. So the distance from here is y squared. So then, there's not to look at. So.
Talk about R out.
This was 7, right?
That was 7.
Yeah. So then for the outer one, it should be 7. Should be 7 minus y squared.
Okay, and then what do you think for the inner?
For the inner one, it should just be, well, it should be 7 minus y.
Okay. We'll take a vote. That's good. Thank you.
Yo, give this man an applause.
What do y'all think? You got an applause. They must agree. Looks good to me. Yes?
Yeah.
Yes? So our outer radius is that distance, 7. Take away that distance, y squared. Inner radius is distance from here to here. 7, take away your y. So our formula, integral, our pi integral 0 to 1, outer 7 minus y squared, squared minus 7 minus y squared dy. Is that all right? Okay. Awesome.
That visualization was awesome because I'm pretty sure if it was like any other, to be honest, I think if it was any other professor.
Well, let's not go there. Let's just go.
Saying your way's better.
I'm not going to say. What did I say? I said I don't have notes for one reason. I show it to you in a way that it makes sense to me. I'm not going off of notes because I am truly going off of the way I think about this. All right? This is the way I think about it. I learned it a different way. But it was after I understood it that I said, why not just think of it this way? I don't know. It's all personal. It's all personal preference. Okay, good. I'm glad it does. It made sense to me this way also. Okay, so now that you seem to get this, let me ask you to do this one. I want you to look at y equals sine x. And I just want you to consider that y equals 0. So I'll draw it for you. I'll draw it for you. I just want you to be looking at this right here. The first arc of sine. The first arc of the sine function. And I want you to just consider the volume about the y-axis. I want you all to consider that amongst yourselves, talk to each other, and I want you to consider it for the next 3 minutes, and then we're going to talk. I'm not talking to you, sorry. You can talk to your friends. Talk to your friends. And then I'm going to ask you to explain what you're thinking. Okay? I didn't mean that to come across so rude. I'm sorry. Do not talk to me. You can't write this answer down. I challenge you to write it down. Okay, let me see it. Well, go. See what happens. You have 3 minutes. Well, you're saying you have it.
Yeah, but I don't know if it's
Let me see.
You said over the x.
Over the y-axis.
This one, right?
Yeah.
This from 0 to 1.
Mm-hmm.
You stack the pi. The 0 squared because this is c. It's pi squared because this. Oh, it will be sine. Whoops.
No? Yeah. I'm giving you this problem because it's difficult.
So your integration though.
What did you put? Sine what? X? And then what? At the end, d what?
Do what?
You can't have x's and y's like that. Right? Do you? Okay. I want you to think about it because this is a good question.
When you make the rectangle, it has to go
Yeah, if this was x-axis, we'd be done by now. This would be over. Yeah. Okay.
Technically it's 0x.
That's what I'm saying, yeah. That's weird.
You got about 15 seconds, then we're going to talk.
Yeah, that's what I'm saying. Because when you get just like that, that's why it's a more complicated question.
Okay. So now, I'm so sorry. Would you like to share? No? No, it's okay. So you were going to say something initially. Can I ask you what you were going to say now or no?
How it doesn't pass
Okay, good. So I think you recognized right away, at least one person recognized, that if we're going to wrap around the y-axis, then our axis of rotation is here, right? And that means if we're going to use washers, our rectangles must be orthogonal to that. So our rectangle would go this way. And if you put your rectangle this way, you do not have a right function and left function that are distinct from one another. It's the same curve, right? Or it fails the horizontal line test, right? This curve fails the horizontal line test. So then you might go, okay, well, I'll solve for x, right? I'll take this and I'll solve for x. Did anyone get to that point where you wanted to take that and solve that for x? So you do arc sine on both sides and you get arc sine of y equals x. Okay, there's a problem with that also, because when we define the inverse trig functions, every single inverse trig function required that we do a domain restriction. When we define arc sine, we had a domain restriction. We had to cut the sine function between negative pi over 2 and pi over 2. So you're not even allowed to talk about arc sine if you're outside of negative pi over 2 and pi over 2. So you can't do that. So maybe you say, okay, I'll just take half of it. But I want that rotated too, right? Do you see that this is very problematic?
Yes.
And the methods we have right now, we don't have a way of doing this. Okay? Yet. So now we introduce a new method. It's called the method of shells. Not washers, shells. And what shells allows us to do is take a problem like this and say, I have an axis of rotation that's vertical, right? Method of shells allows me to find the volume if my rectangle is parallel to the axis of rotation. I will be able to do this, okay? But what's the method? What's the formula? Because it's not the same as the method of washers. Yes?
So it wouldn't have worked if we set the domain restriction to pi over 2 and set that as a function?
Well, you would have, yes, you could have. You could have done that, and then you would have just wrapped half of it around.
And then doubled it.
This stuff goes on a larger radius around, doesn't it? Imagine like physically, if I wrap that around, I'm going to have this little solid in here, right? That stuff goes in a larger radius, so you're going to have more volume, aren't you? So it's not as simple as just doubling it. Got it? Okay, so, pardon?
Like individually, as in like do everything that we were doing for that one part and then do everything we're doing for the other part and add them together, or you can't do that?
You might have been able to do it by going from here to here, and then you would have to use a different, what we call a different branch cut of the inverse function, but now we're starting to get way too complicated. Like it's starting to get too much. So there's a better way, and it's shells. So yes, could you have like beat this to death and finally got it maybe? Yes, maybe, but you would have to have been very comfortable with how you have to change the definition of your inverse trig function, change its domain restrictions. So it would be stuff you've never done, basically. Okay, so let's take a quick visual of how shells works, okay? This is how shells works. I have a not as good visualization of this.
Can we get all these things you have from Wolfram?
Some of these are mine, some of these aren't. Let me see. They have, Wolfram has this thing called a CDF player, CDF, it stands for computable document format, you know, like PDF, it's CDF, and you can download this CDF player, and then you can go to their demonstration projects webpage, and you can just type things in, and you can download the demonstrations, and you can manipulate them and do all the things I'm doing. You just can't get into the code. So look at this picture. This animation's not as good as the one we've had before, and it doesn't even appear to want to work. I guess this will work. It's just not as good as the ones we've done, the ones we've looked at before. Can you all see the curve here?
Yeah.
Okay, this curve is kind of like the sine curve that we're talking about. And if I take rectangles that are parallel to the axis of rotation, if I wrap one of these rectangles around like this, I'm going to get, or let's look at this one, it's easier to see. If I take that rectangle and wrap it around, I get this object that looks like this. Okay, like that sushi, yeah. Okay. And what we want to do is we want to have more and more rectangles, so Riemann sums, right? We want more and more, and we wrap them around. We want an infinite number of them wrapped around. If we could do it, if we could do an infinite number of them, man, my computer is really not happy. There we go. Oh, I hit the wrong one. If we could do an infinite number of them, then this would no longer be jagged edges. It would be smooth here, and we would wrap it around. Now this comes all the way around, okay? But it's cut in half so you can just see it. Do y'all see it? Okay, so we have this new shape. Now remember when we did washers, we had this shape, didn't we? We had that shape. And so what we did is we said, well, this is the big one, and then take away the small one, right? And we came up with formulas for each of these. And to do that, we just used the formula for the volume of a cylinder, pi r squared h. Now this, you could argue, maybe does look like a washer. I mean, it's just a really big, tall washer. But we call this a shell, all right? All right, this is a shell. Now let me show you how we're going to get a formula. Because we have to get a formula like we did here, right? Yes? Okay. So I'm going to go back and draw this picture. I have some function here. I'm going to take a rectangle, vertical like this. I'm going to be wrapping this around the y-axis, like this. Okay. When I do that, I'm going to redraw my shell. When I redraw this over here, it's going to look like this, right? There it is. So my axis of rotation is right in there, isn't it? For that particular shell, like it goes like this, okay? Now, I'm still looking between A and B. I'm still going to be moving my rectangles left and right, yes? So how do we get this formula? Well, here's what we do. We come in here with this magic pair of scissors, and we cut this thing, okay? I'm going to cut it, I'm going to roll it, and I'm going to lay it out flat. And when I do that, it's just like this three-dimensional slab or something, right? It's like a box. Yeah, so I basically did this. Oh, this one's better. Basically did this. I took this, right, that shape right there, and I cut it, and I just laid it flat like that, right? Now, this is just like a box, right? The volume of a box, length times width times height. Okay, let's start with the easy one. What's that little thing right there? dx. That's dx because when I wrap this around, the thickness of it is this thickness of the rectangle, so that's dx. Is it too late to do? No, I don't think it's too late to do this. Y'all are, seem to be following me. Can I make this a little shorter and put a bottom function in here? Can I put a g in here? Is that all right if I do f and g like that? So I'm wrapping just that thing around? Okay. You sure? That's all right? Okay. So now, how tall is this? That height, which is the height of the rectangle, which is f minus g, isn't it? Okay, so this is f minus g. Those are the two easy pieces. This next piece is the hardest one, and that's this distance right here. What is that?
And that'd be A to B minus the.
A minus A 2AB.
Here to here, right? Here to here is the circumference of the circle, isn't it? What is the circumference of a circle? 2 pi r? 2 pi r. So 2 pi r is this, right? This is 2 pi r. However, what the hell's r? What's r? Well, here's my axis of rotation, right? My axis of rotation is here. R is the distance from here to here.
Oh, it's A to B.
It's the distance from the axis of rotation to my rectangle, right? To my rectangle. Now, where is my rectangle? It's moving, right?
Yeah.
It's always moving. It's moving between where and where? A and B, right? But what is the variable that is moving? Like what is it like if I asked you to go to this rectangle, right? You're going to go out this direction how far? What do we call that? Would we call it A? Is that A? No. Is it B? It's just X. It's X. I know it's simple, right? But it's X because doesn't X go between A and B? Like as you do the summation, you're basically moving. Like when you're here, this should be here, that's A. And that should be B because I put the intersection in there. But when you start with the rectangle that's all the way at the left-hand side, then what's X? What's your X coordinate when you're all the way at the left side? X would be A, right? And then as you move along, right, your rectangle is a distance of X all the way until you get to B. That's what the integral is doing, A to B. It's allowing your X to move, right? dx, it's with respect to X. We're letting X move from A to B, right? Okay, so the distance, where the position of your rectangle is X, and that's your radius. So this becomes 2 pi x. Does that make sense? I'm out of time, but we're right at the formula. Okay, we're right at the formula because yes,
Don't
what?
do x minus a because you're not completing
The axis of rotation is here, right?
Oh, okay, got you.
So I'm trying to rotate from here to that rectangle, and that distance is exactly x. Because this is 0, right? 0, that's A, that's x. X is between A and B. All right, that's the formula for this. The volume of that is that times that times that, right? That times that times that. Length times width times height. 2 pi times x times f minus g dx. I just changed the order. So it's 2 pi times x, that's that, times f minus g times the dx. Length times width times height. Now that's the volume of one of those little slabs. What do I want to do? Have an infinite number of them, add them all up. So I bring the integral in, right? So if I take the integral, so this is the shell method. If I do the integral, it's going to be this formula, right? I can pull 2 pi out, can't I? So 2 pi can come out, but here I'll have x, then I'll have f of x minus g of x, and then finally dx. And what is going to go here? A to B, because we're letting x vary between A and B. And this is the formula for shells. I know I'm out of time. But the problem that I gave you to think about for 3 minutes, sine x, right? Y is sine x. Our rectangle's like this. Our axis of rotation's here. Our top function is sine, right? Our bottom function is 0. So if I go here to this formula, it's going to be 2 pi integral from where to where? 0 to pi. That's what I gave you, right, in the picture. And then x, which is just x. It's the variable. And then f, what's f? Sine x minus g, which was 0. So just sine x dx. That's it. Integration by parts is what it would take for that. See that? Isn't that nice? So that method is, when we're looking at these problems in a test, what you're going to want to do is look at your region, and you're going to say, look, what's easier? Is it easier for me to do washers, perpendicular, Or can I just use shells? And you're free to use whichever one you want.
Are we gonna use shells? Is that on the homework?
Shells is not on this homework. It's its own section actually, but you will have some problems that will give you for shells. So do your homework for 8.2, all right? 7.2, sorry, 7.2. For what? I don't know of one. No? Parallel? Yeah, no. Give me a second. Let me. Oh, is that the sheet? Yeah.